right, so hopefully this will stay somewhat in focus. All right, so what I want to do today is I want to try to combine both the theoretical and the applied and talk about some mathematics that's useful in both. So what is the big lie from Calc 2? You can integrate. Okay? In general, you cannot integrate. If I really cared, I would have gone back and checked the video from the first day of class. Did I bring the dartboard down? I did not bring the dartboard down. Okay, there have been complaints about violating zero tolerance policies for weapons. When I teach Calc 3, I sometimes bring a dartboard and have people throw darts at the board. This is actually how we integrate in the real world. For those of you who are going into finance, this is extremely important. This is how you do the 100-dimensional integrals that arise. So it's called Monte Carlo techniques. It's considered by many to be the most important idea in 20th century mathematics. Okay? Obviously, whenever you hear a statement like that, that's fighting words. But this has a legitimate claim to that title because of how many problems it can be used for. So one of the reasons why this is so useful is because it helps you attack a variety of other problems that otherwise we just wouldn't know how to evaluate. So the idea is, how do you evaluate an integral? In one dimension, what are you taught? So you're taught compute the antiderivative. Well, we have things like the Gaussian, which doesn't have a nice antiderivative. So even if we stay in one dimension, something like that is going to be very difficult. Now, if I have the Gaussian, I can plot it like this. And eventually, there's so little probability in the tails, it's not going to be that bad. Maybe I can come up with a series expansion. Maybe I can integrate the series term by term and get a very rapidly converging answer. And for the Gaussian, we can do this. This is called the error function, the ERF function. It's extensively tabulated. It has really good convergence property. The key idea in that was to note that if you're integrating the Gaussian, what is the area under the curve up to 0? It's what? It's 1/2. So what you really do is you only need to calculate, say, the integral from 1/2 to any point like this. You calculate or do it symmetrically and then divide by 2. So you calculate what's the area that you're in a certain band like this. And if you can calculate this band, you can calculate the area between any A and B by just playing a subtraction game. So if you want to find the probability that x is in AB, this is the probability that x is in the interval -infinity b minus the probability that x is in the interval -infinity a. And so if you can just do certain nice symmetric intervals, it turns out you can do anything. So there are ways to do it in the special case of the normal in a function where you have a really nice expression. Unfortunately, even that is not going to be the case in general. Also, we are going to have integrals in 100 to 200,000 dimensional spaces. In general, this problem is going to be far too difficult to solve exactly. Some of you might remember things like Simpson's rule, the trapezoid rule, ways to approximate using either rectangles for Riemann sums or Simpson's rule using trapezoids. And the more you take, the better job you do. You have approaches like this. But as your space gets higher and higher in terms of dimensions, now you've got to think, okay, I've got a 15-dimensional object. How am I chopping everything up? What we're going to assume is that our region is nice. So what does it mean to have a nice region? So I want two things to be true. One, contained in a finite box. And two, easy to tell if in or out. So in the simplest case, here's some rectangle, and here's my region A. And maybe I have two curves. Here's the top curve, f1 of x. Here's the bottom curve, f2 of x. And my region is all the points from this A to this B, where f2 of x is thus equal to x is thus equal to f1 of x. These could be very difficult functions. All I need to be able to do is evaluate them and say, is my point between f1 and f2? So if I have a region like this, I can calculate the area very nicely. Now again, the dream in something like this is that you would actually have antiderivatives. but we may be in a situation where we don't have antiderivatives. So the idea is we're going to use the central limit theorem or Chebyshev to evaluate these integrals. And it's going to go as follows. So, okay, let me know if I'm out of focus. So we introduce indicator random variables. Indicator random variables. So we'll let IA of x be 1 if x is an A and 0 if x is not an A. Okay? And we have some giant box here, B. So the probability you're in A is what? So what's the probability if all points are equally likely to be chosen if I choose a point at random that I'm in A?
The area of A.
Not quite. The area of A divided by the area of B. If all points are chosen equally. Fortunately, this is the simplest possible random number generator. We just need to be able to choose numbers uniformly at random. We've talked early in the semester, we had a great homework problem, using the CDF method of how we can simulate any random variable with a nice CDF so long as we can simulate uniformly. Well, here it's enough to just stay at uniform. And so, I can choose my x coordinate uniformly over here. I choose my y coordinate uniformly from there. I can now get a point, and I now see, am I inside the region? The probability I will be inside that region is just the probability of A over the probability of B. Without loss of generality, let's choose units so that the area of B is what? 1, right? So choose dimensions so that the area of B equals 1. This is just going to simplify some of the formulas. Is it absolutely essential? No. But I might as well assume my box that I'm bounding everything in has area 1. If not, I just rescale things. Okay. It's very important that I am not dealing with an infinite. We did the 2-envelope problem earlier this semester. And the difficulty there was we were trying to put a uniform distribution on the entire space. If a function travels over many different regions, you might want to sample in a bunch of different boxes. I am not saying that this is going to be the optimal way to simulate the area. There's a beautiful subject, dynamic programming, where if the function isn't changing that much, it's foolish to spend a lot of time sampling there. How many of you have taken differential equations? Not many. Did you do like the Euler method to numerically approximate solutions? Or the Runge-Kutta method? You take the value of the differential equation at a point, you use that to guess the next value, and you keep iterating. What you're doing there is you're sampling at uniformly spaced points. If your function isn't changing that much, it's wasting a lot of your computational time to keep sampling at those points where the function isn't moving. You want to do more sampling where the first derivative is large and less sampling where the first derivative is small. You can play refinement games like that over here and make things better. Okay? You can also use special lattices to make sure that when you choose points at random, your points are actually well spread out. It is possible that when you're choosing points at random, maybe you're just unfortunately clustering a lot of points here more than you would expect. And if that's the case, you're not going to be spreading uniformly. Can you think of a good way to make sure I'm sampling the whole space uniformly if I'm taking 100 points?
Draw 100 boxes throughout the thing and then generate a random point in each box.
Yeah, so do like a 10 by 10 grid. So if I know exactly how many points I'm going to do, I can make a really nice grid. The problem is, what if all of a sudden somebody says, you know what, we need a slightly better answer. I'm going to let you run the program a little bit more. You can get another 30 data points. My whole grid was set up on the knowledge that I'm doing exactly 100 samples. Now that I have the extra 30, it's not designed to build that up nicely. There's actually a really nice way using the Fibonacci numbers to construct a lattice that if all of a sudden you can run more computational time, you actually have exactly what you need to put in the points in the most beneficial way possible, or at least a very beneficial way. So I'm not going to go into all the subtleties of the subject. I want you to be aware of what's out there, especially if you're going off into the real world and you're going to have difficult integrals to evaluate. There's a lot of techniques out there, and there are ways to make your answers better and faster. If you're going to be spending your life running simulations, a 20% decrease in runtime is huge. Okay? Your models will run faster. You'll be able to simulate more. You'll be able to gather more data. All right, so we're going to let xi equal 1 with probability area of A, and I'll write divided by 1 because we're assuming B has area 1, and 0 with probability 1 minus area of A over 1. Sure. Okay, so I'm basically choosing a bunch of points uniformly at random in the box. Am I still in focus? Okay, so I'm choosing a bunch of points uniformly at random in the box. What quantity do you think I should study? What should we study? I'm sorry? The mean. The mean of what? So you want to study what? So the expected value of xi is just going to be the area of A. And the variance of xi is just going to be area of A 1 minus area of A. Just because I have a nice binomial random variable. So if I just choose one point at random, the probability I land inside my region is area of A. I'm going to choose a huge number of points. So choose x1, x2, xn. So I choose a bunch of points. What should I look at now that I have all these points? What should I study? Okay, so what should I look at? Yes, the mean. So let's study x1 plus xn divided by n. Let's call that yn. What's the expected value of yn? Area of A. What's the variance of yn? Since they're independent, the variance of a sum is the sum of the variances. I've got this 1 over n down below. If you multiply a number of a random variable by 5, the variance increases by 5 squared. I divide by n, the variance decreases by n squared. So I have it's n times the variance of xi divided by n squared. So it's going to be area of A 1 minus area of A divided by n. This is wonderful. The mean value is going to be really close to the true area of A. Why? Well, the standard deviation is going to be, some universal constant depending on the area of A divided by square root of n. As n gets really, really large, the amount we're missing by for the area of A is going to be negligible. This is a phenomenal way to evaluate integrals. It is equivalent to throwing dots at the dartboard and seeing what fraction of your dots strike the target. And you even get estimates of how rapidly we converge. I'm not going to go into all the details now. What results could we use to try to get estimates? I can think of 3 things we could use. What are the 3 things we could use? So we could use central limit theorem, Chebyshev. Nope. I mean, we could use Markov, but Markov sucks here. You could use it, though, because they're non-negative. We could use the fact that sums of these binomial, I always get this mixed up. These are Bernoulli processes. The sum of Bernoulli random variables is a binomial random variable. We actually have an explicit formula for this sum. I would much rather use the central limit theorem approximation if n is of the order of 10 to the 5, 6, 7, 8, 9, rather than using the exact formula and having to deal with the binomial coefficients. The easiest way to attack this is to say this is converging to a normal with this as the mean and this is the variance. And then we would have incredibly accurate results of how close this is to the true value. So as a nice exercise, I strongly suggest that you go through and actually see what kind of estimates you would get. Okay. Any questions on this so far? Okay. Could you put up the screen? It's the first one closest to the blackboard. Oh, sorry, there's two blackboards. Yes, that's not useful. Okay. So I've written a computer program to, so I'll go like this. All right. Is it focused? It's a little too tall. All right, you might have to just adjust the camera a little bit. Who thinks they can adjust it without breaking? All right, I've written a computer program. You might want to stand up. Just physically touch the iPad. Okay. I've written a computer program. I have some region. It's going to choose dots. If you've seen this calculation before from 150, don't speak up. Okay. Anybody have any idea what the region is? Red is if it's inside, blue if it's outside. Anybody have any sense of what the region is? You've got 2 data points. That should be more than enough. All right, so as soon as you figure out what the region is, yell it out, and then yell out what the area should be. And it hopefully will, it might be telling us the running total of what the area is. Does it say it at the top? Oh, all right. I thought I had, it resizes things.
Professor, I think it's a little too bright. It's not showing.
It's not showing. Is that better?
No.
No.
It's still just like a white screen.
All right, well, that's the disadvantage of the people who are taking it at home. All right, can you figure out what it is? It's an ellipse. And at the very top, it's giving you a running tally of what the area should be. And so I can speed things up. It's done about 700 data points. For those at home, tough. So now we're in 3,000. All right, so I'll go all the way to the end. All right, so here is almost 8,000 data points. And the reds are the ones that are inside. The blues are the ones that are outside. All right, I'll move a little bit over here. These points are chosen uniformly in the square. So here I think my square has area 2. What you'll see is there are large regions where I don't have points. So when you choose the points uniformly at random, you actually will have clumping happening. And so it is actually better to use some kind of lattice structure to try to have the points spread out more uniformly. If I was missing something through here or had extra stuff over here, I would miss stuff like that. However, to first order, this does a really good job, and it's very easy to code. This was something we saw with the tic-tac-toe problem. It was much easier to just randomly simulate a drunk game of tic-tac-toe than to actually go through and exhaustively go through all the possible games. It's not that much more work, but it's a little bit easier. And sometimes it's easier to just write the simpler code, especially if you have enough runtime to go a little bit further. Anybody recognize the number 1.54?
Pi over 2.
It's roughly pi over 2. So the question is the area of this ellipse pi over 2? So I'm not going to get into too much of this right now. If there's time at the end of class later today, I will talk a little bit more about that. But there are ways to try to sniff out the formula from this. And we did this when I taught Math 150 a couple of years ago. If you really want the full details, I'll just put up a link to that lecture. All right, if you could put the screen up. All right, so what I want to do now is I want to shift gears, and I want to continue on this theme and talk a little bit about multivariate distributions. So we haven't done too much on multivariate distributions so far this year. Okay. So a multivariate distribution is a distribution where we have, say, 2, 3, 4, etc. parameters of interest. All right, right now in the Gaussian, we've only looked at Gaussians of one variable. But of course, you could play the game and you could say, well, maybe I have a Gaussian in 2 variables. I have inputs x and y. The main difficulty, of course, is that the integration becomes significantly harder. So what I want to do is I want to talk about one of my favorite problems in mathematics, Buffon's needle, and talk about how you would do this as a multivariate problem, as well as how you would do it without calculus. So how many of you have heard of Paul Erdős? He's basically one of the rock stars of mathematics. He's dead now, but if you know what the Kevin Bacon number is, how many movies do you have to go through before you've been in a movie with somebody who's been in a movie with Kevin Bacon? In mathematics, we have the Erdős number. Have you written a paper with somebody who's written a paper with somebody? My Erdős number is 2. I have met Erdős, phenomenal guy, over 500 co-authors, over 1,000 math papers, most of them worth writing, if not all of them worth writing. Absolutely phenomenal, the amount of mathematics this person generated. Traveled all over the world, did not have a permanent place, just went around doing mathematics. Okay? Absolutely phenomenal person. This is a math class, this is not a religion class. I do not, for the most part, talk about politics or God or religion, but I will relate Erdős's advice. As a mathematician, you do not need to believe in God. By all means, feel free to pray to God or whatever you want on exams. You do not need to believe in God, but you do need to believe in the book. So how many of you have ever heard the expression the book before? Okay, what is the book?
It's like God's list of all the mathematical proofs.
Yes, it's the book God would have with the best proofs of all the theorems. It's the elegant proof, the one, the one that makes you react like that. And so you don't have to believe in the existence of God, but you do have to believe in the existence of the book. So the very first chapter in the book, and I actually have it in my office, is, because that could be misinterpreted. I do not have anything from the Supreme Deity that I'm willing to admit. What I have is I have a book that was published called The Book, a human approximation to what we believe the Almighty's book would look like. Chapter 1 of that is 6 proofs of the infinitude of primes. These are supposed to be beautiful elementary proofs of the infinitude of primes. So we are first going to do Buffon's needle. We will do it as a calculus problem, but I will also show you how to do this without calculus. And this is one of the chapters in the book. So Buffon's needle. All right, so here is the following situation. You have an infinite grid of vertical lines. All of the spacings are exactly d units apart. And you have a rod of length L less than or equal to d. And you throw the rod down, and you ask, what is the probability the rod hits a line? Is it possible for the rod to hit 2 lines? Why not?
It's length less than d.
It's possible, right. It can't hit 2 lines, it's too small. It could hit 1 line infinitely often if you happen to land exactly like that, but the probability of that is 0, so we're not going to worry about it. You could, of course, study the problem for longer length lines. It becomes a little bit harder. You can then ask, how many times does a rod hit? And the question is, what is the answer? This is a nice, well-formulated problem. So before we solve it, I want to see if we can figure out what the answer would be. On a personal note, I was the president of the undergraduate math club at Yale many years ago. And I was taking probability, and one of my jobs is to find people to give talks. And I was begging the instructor for my probability class. I said, you can talk about anything. We'll pick up the pizza. We'll do all the cleanup. All you have to do is give a talk. He says, you'll do all the cleanup? Yes. OK. So he talked about Buffon's needle. And what he did is he brought spaghetti. And we had a grid floor. And he threw the spaghetti up in the air so that we could count how many times it hit. And then he said, let's see if it makes a difference whether or not the spaghetti is sticky and wet. And I give him credit. He actually worked throwing wet, sticky spaghetti up onto the ceiling in a talk that I promised to clean up. I think some of the spaghetti is actually still on display in that classroom at Yale. I did not do a great job. Oh, wait, this is being recorded. I'm sorry. All of the spaghetti was cleaned up, and the room was returned to the pristine state it started with. All right. Guessing the solution. What parameters do you think will play a role in the solution? D. What else? L. Any universal constants you think might play a role? E. What else? Pi. Anything else? Right? I mean, I love logs and products as much as the next guy. I really do not see any products going on here. I don't really see where the e is going to come from. For pi, I normally think of circles with pi. Really don't see any circles here. That's not to say that these constants don't appear. One of them, in fact, will appear. Almost every good math problem, eventually you see one of these two numbers. All right, can anybody tell me how the answer should depend on L and D? Yes?
Seems like the probability that a line would be proportional to like L over D.
Good. Remember to email me. Answer depends only on ratio L over D if L is less than or equal to D. If L is much larger than D, it may still only depend on the ratio L over D, but at least when L and D are small, this is very plausible. And the reason is if I double D and I double L, if I triple D and I triple L, can I tell any difference? No. So before doing any analysis, we have a rough idea of the answer. Okay? So we know the answer if we are just concerned with the dependence on L over D. It's got to be something L over D. So probability we hit is some constant L over D. Okay? Or expected number of hits is some constant L over D when L is less than or equal to D. We can actually guess what that constant is if instead of considering a rod, we consider a nicer shape. So let's try to think about how we're going to choose coordinates for the point, for the rod that we're dropping. We have some random variable. It's the location of the rod. So we have our grid, and now we're going to throw down the rod in some way. So we need to determine coordinates for choosing the rod to be thrown uniformly on this infinite grid. So again, whenever we see an infinite, we should recoil in fear and horror. We've got to somehow find a way to make this finite. I do not want to consider throwing a rod uniformly on an infinite grid. I'd still be cleaning up. Okay? I want to consider the rod being thrown on a finite patch and claim that all we have to do is understand what's going on in a finite patch and we're done. All right, any thoughts of what that finite patch should be?
One space of L and D.
So one space of L and D. Okay, and what are we using to determine the rod? Because again, you can see over here that this rod can actually go across two different spaces. But it's not going to hit both spaces, so it might be enough to just consider. But you won't have the rod entirely contained in the whole space. So you've just got to think, what should we use as our variables or coordinates for the rod?
Two endpoints.
So one possibility is we could do the two endpoints, which will require 4 pieces of data. But of course, if I give you 4, how many pieces of data do I really need to determine a line? To determine a line, I want to answer first the 2 endpoints. So if I use endpoints, we need 4 coordinates. But how many points determine a line? But what do you need? A line is of the form what? Slope intersect. Y equals mx plus b. We can do it with 2 coordinates. So one possibility is we can do 2 coordinates for the line. That will give the line, but I need to know where the line is starting. What else could we do?
The midpoint and angle.
Good, midpoint angle. Midpoint angle. So I think that's the most natural coordinate system to use. What can you tell me about the location of the midpoint of the line? We have a lot of symmetry here. Yes?
The midpoint will always
Okay, so we can always standardize and say the midpoint is always going to be in one interval. And in fact, we can go a little bit further. So we'll assume the midpoint is somewhere in this one. And here's my x-axis, here's my y-axis. We can make an assumption about one of the two coordinates of the midpoints. One of the two coordinates, we can assume we know its value.
Y.
What is y? What can we choose y to be? Anything. So what would be a good choice for y? 0. We have complete vertical symmetry. Right? If you look at this problem, I can shift the line up and down, and if I shift it up and down, it's not going to change. So without loss of generality, you might as well assume the center of the line lies on the x-axis. So here's the line y equals 0. Here's 0, here's d, here's 2d. The center is going to land somewhere between 0 and d. But I claim we can make one more assumption. We can simplify things a little bit for the x-coordinate. What's the largest x-coordinate we need to consider? You can say it's between 0 and half of d, because by symmetry, if it was beyond d, we could just flip, and that's not going to change how many lines it touches. It will change which line it touches, but it won't change how many. So without loss of generality, we're making a lot of simplifications here. And the more simplifications we make, the easier the problem is going to become. Okay, so now we have y equals, so this is the center of line. So y equals 0, 0 less than equal to x less than equal to d over 2. Now we need to do the angle. Okay, am I still in focus? Okay, so now we need to do the angle. What can you tell me about possible values of the angle?
It has to be between pi over 2 and 3 pi over 2, because if it goes like this way, then
Okay.
that's the same as it going this way.
Okay, so instead of doing pi over 2 to 3 pi over 2, people would normally do minus pi halves to pi halves, or 0 to pi. It's got to be in some region of at most 180 degrees, because if I have, if I have it like this, if I call this angle theta, that's the same as this angle here, which is theta plus 180. So I can always assume theta 0 less than equal to theta less than equal to pi. So again, we're restricting the space a little bit. Okay, any questions so far? We're going to make one more restriction. Question or?
Well, I was saying, the angle, did you just say that it's between 0 and pi over 2?
You can. Why?
Because if it hits the line like that, it's going to hit the line with the angle 180 minus.
Right, you could always reflect. So if I have my line like this, I can always reflect it and consider the line like that. And so if you want to simplify things even further, without loss of generality, 0 less than equal to theta less than equal to pi halves. Why do I care about all this? I may be integrating sines and cosines. It shouldn't be surprising if sines and cosines come into play for this problem. And when you're integrating, you need to, if you want to calculate probabilities, you need non-negativity. You might have to put in absolute values. I don't want to deal with absolute value signs. If I restrict my angular measurements, it's going to make life a lot easier. So now I have a space. So here's my space. The density f of the density f of x theta, that's a capital theta, of x and theta is going to be some constant if 0 less than equal to x less than equal to d over 2, 0 less than equal to theta less than equal to pi halves, and 0 otherwise. So all we have to do, we have a uniform distribution over a rectangle. We have to figure out what's the normalization constant. Well, the rectangle, here is the point 0, 0. Here's the point d halves, pi halves. So the area of the rectangle is d pi over 4. So if I want to make this a probability distribution, I divide by 4 over pi d. So that will give me a uniform distribution on this little rectangle, which is equivalent to choosing the rod to land anywhere at any angle on the whole grid. All right, so we have a multivariate distribution here. It depends on 2 parameters. It depends in the nicest way possible. It's a uniform distribution, but it's at least a legitimate, honest to goodness, 2-variable probability density function. If we want to calculate the marginal of x or the marginal of y, we could just integrate the other ones out. Are x and theta independent here? Yes. So you should see that they're independent just from the physical geometric construction of how we're doing it. But since we have the joint probability density function, we could calculate the marginals. We could integrate out theta and get the marginal of x. We could integrate out x and get the marginal of theta. And then we would see the density of the pair is the product of the densities. So this is a great way to review a lot of what we've done throughout the semester. So this is what I want to do for the last 2 weeks, is I want to do fun problems that combine theory and applications as much as possible and review the concepts we've been developing and see how they're used. So we can check the independence many different ways. So all we have to do now is calculate what's the probability the stick actually hits a grid. Okay? So now we come back. Let me just make sure I do things the right way. Okay. So what's the probability of a hit? Well, x goes from 0 to how much? One possibility is we could go all the way up to d over 2. But if we go all the way up to d over 2, can we get a hit? No, remember, so here's d over 2, and we have L is less than or equal to d. The only way we can get a hit if x goes as large as d over 2 is if the rod is perfectly aligned with the x-axis and L equals d. If L is any shorter than d, it won't reach. So we could integrate all the way up to d halves. It's just the probability of a hit will be 0 in those regions, and then I've got to start doing all these different things. So how high should x go up to? I shouldn't go all the way to d over 2. How high should I go up to? L over 2. So we integrate up to L over 2, no hit if x is greater than L over 2. Now we have to worry about the angle. All right, so theta goes from 0. We know the largest it can be is pi halves, but if it's pi halves, the only way we can have a hit is if x equals 0. So in general now, let's say we're at some value of x. This is the center. So we want to figure out what's the largest angle we can take and still have a hit. An angle of 0 definitely works. Well, for it to just barely hit, this coming down here has to be L over 2. This has to be a right angle. And then this will be our angle theta over here, which by symmetry is the same as this one over here. So I'll draw the picture a little bit larger. Here's x. Here's L over 2. Here's theta. So if we're going to get a hit, we need L over 2 cosine of theta equals x. So theta equals arc cosine of 2x divided by L. So arc cosine of 2x divided by L. But now, what's the probability of a hit? How many hits? It's going to be just 1. And now we put in the density. The density is 1 over, I'm sorry, not 1. Is it 4 over pi d? It's 4 over pi d d theta dx. And again, I really like putting names on my integrations to make things a little bit easy to remember. All right, any questions so far? All right, so here's the probability of choosing that pair theta x. Here's the hit. It's going to be 1 in that region. Otherwise, if I went to the whole bound, it would be 0 otherwise. So I'm just saving a little bit of time. All right, the theta integration is really easy. What's the integral of d theta? 1. What? No, not 1. It's just the integral of d theta is theta. So I get x goes from 0 to L over 2. And then I have the integral of arc cosine of 2x over L minus the arc cosine of 0. The arc cosine of 0 is 0. All right. Now you just have to integrate arc cosine. I'll let u equal 2x over L. And so now I put a 2 over L here. I put an L over 2 here. I get 2 over pi L over d. Integral u goes from 0 when x is L over d, u is 1, arc cosine of u du. Anybody remember the antiderivative of arc cosine? I would yell at you if I actually remembered it myself. So the antiderivative of arc cosine of u is u arc cosine of u minus the square root of 1 minus u squared. Yes. This is not a natural integral, but it's not unnatural to guess something like this. We've seen a trick like this when looking at the integral of x log x when we were doing Stirling's formula. So when we were trying to find the antiderivative of natural log of x, we guessed x log x because when we do the product rule, when the derivative hits the x, we then have the log of x surviving. So I want to get arc cosine of u. Hell, let's try a u arc cosine of u. When the product rule hits the u, I get an arc cosine. I'm then stuck with the u times the derivative of the arc cosine, so I have to adjust. And that's this piece over here. Yes?
Isn't arc cosine of 0 not 0? Because cosine of 0 is...
Oh, have I made a mistake there? Okay, I will leave it as arc cosine of 0 just to be safe, because we're going to be really close on finishing. So let's see. I want, let's see, the angle whose cosine is 0. Should that be pi halves? Yeah, we've got, I almost surely am making a small trig mistake here. I don't want to worry about it. So this is not the right way to do the problem. So I'm going to just say, yes, I might be making a mistake there. Let's drop that. Nobody wants to do this antiderivative. There's two solutions. One is to think about this problem better and use the method from the proof of the book. What is the other way when you're stuck with a bad integration like this? What else could we do? So this is one of the most powerful techniques we have from Calc 3. You really only learn how to do two things in Calc 3 for integration. What can we do? I'm sorry? Switch the orders of integration. It's either switch the orders of integration or change variables. That's all we can do. So if you have something like this, try it the other way. The probability of a hit, it's going to be the integral theta goes from 0 to pi over 2, and then the integral x goes from 0 to, now we have to figure out what's the maximum x can go to. Well, if I have an angle, so here's d over 2. Here's my x. Here's an angle of 0. All right? Okay. So what do we want this distance to be? We've talked about this before. How far can this be? L over 2. So we want to go, x goes from 0 to L over 2. All right, so now All right, so now we have, okay, so now, so when theta, okay, so when theta is 0, any x can go all the way up to theta over 2. And then as we start increasing, okay, right. And then this is where things become difficult. Now imagine we have some angle. We want to make sure we still hit. So given an angle theta, how can we make sure we still hit? So yes, when theta equals 0, the maximum x can go up to is L over 2. But now you give me a value of theta, I have to figure out how far over can I go. So I need this to still hit. So what's this length going to be at the maximum? That's going to be L over 2. So now what we have is we have our triangle. Here's theta, here's L over 2, here's x, and we get L over 2 cosine theta equals x. And again, it's going to be 1 times 4 over pi d dx d theta. So it's very similar before, but now we have a cosine instead of an arc cosine. All right? We get 4 over pi d. The integral theta goes from 0 to pi halves. The x integral is just x. So we get L over 2 cosine theta d theta. The L gives us a little bit. We get a 2L over pi d. The integral of cosine is sine. So we'll have sine of theta evaluated at 0 and pi halves, which is just 1. So we get 2L over pi d. So the expected number of hits, or the probability of a hit, is pi over d. I'm going to send you a write-up of the way to do this from a proof from the book. The idea is rather than throwing a line, to say, well, look, if I split the line in half, the number of hits I have is the same as the number of hits from the first part plus the number of hits from the second part. The expected value of a sum is the sum of the expected values. If I split the line into 4 pieces, that's fine. And what I'm going to do is I'm going to take those 4 pieces and put them into a square. If I split into 5 pieces, what object would I get? I put into a regular pentagon. And as I do more and more sides, I'm getting all the angles equally likely. And I'm just moving and I'm just shifting the pieces a little bit. So I'm not going to go through all the details. I'll let you read it. What do you think the most natural shape to use is? Circle. And if you use a circle, if you choose the circle to have just the right diameter of d, so the perimeter L would be pi d, you're going to get exactly 2 hits. And it doesn't matter where you move the circle, you'll always get 2 hits. It's going to then tell us if I want to look at L over d, I have some constant. When L equals pi d, I'm supposed to get 2. So my constant has to be 2 over pi. That's got to be the formula. So I want to just very briefly end with a quick note. Somebody claims to have done this experiment and dropped 3,480 sticks. And can you load the screen? And when he dropped the sticks 3,408 times, he got 1,808 intersections. He claimed that his stick lengths, the ratio of L over d he used, I think, was 5/3. And pi to 20 decimal places is 3.14159265535. He got 3.141592920. So it looked like he did a phenomenal job of evaluating pi. I want to end with the need to be skeptical on any reported data. There's some great stories on this. I'll link to one of them. Somebody said, let's imagine this guy threw one more stick. Doesn't matter if it hits or misses. If he throws one more stick, if it misses, he has this ratio. If it hits, he has this ratio. Look at how many digits of accuracy he loses. So a little bit lower, I've put them in decimal. He goes from basically having 7 digits accuracy to having about 4 digits accuracy. What he did is he took a really good rational approximation to pi, and the evidence is overwhelming that he just faked the data. So if you're interested in stuff like this, not faking data, that you should take Professor DeVoe's class. But if you're interested in, detecting faked data, Professor Gowdy will be teaching a class involving continued fractions, which lead to the best rational approximations to stuff like this. All right, we will do the central limit applications of NCAA on Friday.
It's just not really enough sticks to do that.
Well,
To get that